is that a lot of people here are from Nigeria, or it's like 11 p.m. for you guys, 10 p.m. in Egypt, 1:03 p.m. don't know too much about blockchain, 10 p.m. in Germany, 3 p.m. in Mexico, 11:04 in Turkey, 2:04 in Edmonton. I love how international the hackathon is. It's really cool to see people from all over the world coming here. 3 p.m. in Peru. If you don't hear anything, maybe try rejoining. $8:05 in Ghana. $3:05 in Jamaica, 11 p.m. in Iraq. I imagine a lot of people here don't know much about blockchain. Blockchain is a topic that I think it's pretty niche. I know a little bit about blockchain, or maybe quite a bit. But I do know that a lot of people don't know much about it. You might know like a little bit, maybe like you've heard of cryptocurrency, but otherwise, most people don't know much more about blockchain than that. All right, I think we can get started. And you could stop sharing screen and we can have Alice start sharing hers.
Hi, everyone. Yeah, thank you all for coming in today. I'll get to sharing my screen. Let me see. Then I'll click present. Okay, there we go. Can everyone see my screen?
Yep.
Okay, awesome. Yeah, so thank you all for coming in today. My name is Alice. I am an intern at Metis. We basically provide an optimistic roll-up layer 2 solution for developers to build on the Ethereum. So Ethereum is one of the biggest blockchain-based software platforms where you can exchange their own cryptocurrency called Ether or ETH. And if you don't know what Ethereum is, but today I'll just be going over the basics of what smart contracts are within blockchain, as well as a little bit of what Metis is and how you can get involved if you're interested. And if there's time in the end, then we can go over some questions if you guys have any. So first, why are smart contracts important? The smart contract itself is a contract, but in digital form. So it eliminates the need for trust. And we have the statement, I will X if Y. So this is essentially like an if statement. For example, I'll give you a deed if you buy at the listed price. I will notarize this document if you provide the information. I will record your vote if you validate your identity, and I'll give you the winnings of the Toronto Raptors if they win. There's a large variety of them, and as long as there's a condition, you can put it into a smart contract. So a smart contract by definition is a set of promises specified in digital form, including protocols within which the involved parties perform on these specific promises. It's essentially a digital contract on the blockchain, and it'll run when certain predetermined conditions are met from there. But in other words, you can think of a smart contract like a vending machine. So a vending machine is essentially, where a person selects an item, puts money into a machine, and an item of their choice is dispensed. So we have Alice right here from the Alice and Bob situation. She has $1 and selects a crab cola, puts the money into the vending machine, and then the crab cola is dispensed. And now Alice has her crab cola. So in a vending machine, essentially, you select an item, put your money into the machine, and your item is dispensed. So if we apply the vending machine to a contract with what's called a vending machine contract, you would first see all the available drink tokens, send a transaction to the smart contract, and the smart contract will send back the crab cola token. So we have this vending machine contract on the left and this computer on the right. So you are the computer in this case, and you have an address. you first make a request to get a menu. When you get the menu, you essentially call the smart contract. You say, hey, can I get the menu? The smart contract says sure, and then it gives you the menu right here. This is the menu that is present inside the vending machine where you can have Crab Cola, Crab Classic, Crab Max. There's now the concept of sending a transaction to a smart contract. So in any situation, if you want to change the data, you have to send a transaction. So in this case, the example of sending a transaction would be that I buy something. When I buy something, I am changing the data. So notice when I call something, the ETH that I have doesn't change, the ETH, the cryptocurrency, the payment basically. But when we send a transaction, the ETH changes. One important thing to note is if you're sending a transaction, you're always going to pay ETH for it. And this transaction costs an amount per gas. So the gas price is calculated, and within these values, 21,000 gas is the base fee to pay when you're trying to make this transaction. And 19,000 gas is just how much it'll cost for the machine contract to do everything, including calculating and sending back the Crab Cola token. The 100 way per unit gas up here, I don't know if you can see my cursor, but that's just an estimate when we calculate it in order to find out how much it costs in terms of ETH. So here we have 0.004 ETH. That's just how the total transaction fee is calculated. So this fee is then subtracted after you make the transaction. So we started with 1 ETH, and now we have a little less than half of it when we send the transaction, where we can in turn get that Crab Cola token. So from here, as an overview, here is the Crab Cola token being transferred. But as an overview, it costs gas to send the initial transaction and for every operation. So we have an external account, which is an Ethereum address. It's an address that you and I have. It's like a tracker. And the flow goes to the node and eventually to the Ethereum blockchain. The core of it is for sending a transaction. It'll always go and change the data on the blockchain. So when it reaches the blockchain and changes the data, it'll change the data on all of the computers that are running on that network. So also all of the processing is done inside it. So if you're sending a transaction and you're paying money for it, all the nodes that are synchronized with the blockchain will have to change the data. So for example, say that I am performing a simple operation like 1 + 2 on my computer. That operation will take basically no time. But when you try to do that operation on the network, you're changing the data, and in turn, you'll have to update that data on every single node that is running on the blockchain. That could be thousands and thousands and thousands of computers that are on that one network. So this in turn will have to change the state. And say the transaction is a request and you make a request to add 1 + 2. You would send that request containing the operation, and that costs a base fee, and that bundle is then executed on the network. So this will in turn return this transaction hash, which is like a receipt where you'll be able to see all of the transaction data. So when you're coding this out, there's different types of send, as you can see with one implementation with web3.js and also Solidity. These are just two languages that you can code your smart contract in. But as an overview, here's a general flow. We have to first note that it runs on all the full nodes in the network. So the transaction you're sending, say you're trying to send 1 Ether to someone, it gets converted into this message call, which is then sent to an externally owned account. And with the vending machine contract, when we're sending 0.5 Ether for the Crab Cola token, we're going from the transaction to the message call to the smart contract and eventually to the Ethereum virtual machine or EVM execution. So the EVM execution is just the code that runs. Basically, you want to package that code, send it along, and it gets converted into this message call, gets sent to the smart contract, and then gets executed. So finally, there's also the smart contract creation, where you send a transaction to the contract creation address, and it would create a smart contract and basically execute that code. And that's essentially just creating a new contract. So with this flow, we're using an existing smart contract and we're interacting with it, for example, with the Crab Cola token, as we mentioned before. So programmatically with web3.json, calling the transaction, you could do web3.eth.send transaction, and you just put in the address and the data. Or you could call it with .contract.functionname.send. You specify the function's name. And the third option is when you're buying a Crab Cola token, where you specify by token. In this case, it would be Crab. So just as a refresher, when sending a transaction to a contract, it costs a fee. So we send 0.5 ETH to the vending machine contract, and then we get our Crab Cola token here. And here is just an Etherscan view of a successful transaction. So in this case, we have 0.25 ETH, which will cost 0 in order to send because it's run on the testnet, not on the mainnet. If it's run on the mainnet, then you need to pay a fee. We can list some other properties as well, like the timestamp, addresses when sending and receiving, all the transaction fees, and some other details. This just shows a successful transaction, just like a receipt with the transaction hash, and that can be used to verify if the transaction succeeded or failed. So in this case, it did succeed. Another area is calling a smart contract. So calling a smart contract costs no gas, no fees, and it goes from the external account to the node to the local node blockchain. And this is different than sending a transaction to the smart contract, because when sending the transaction, it interacts with all of the nodes in the network. So thousands and thousands of them. And by changing the data, it'll change across all of it. But with calling this, you wouldn't be changing anything. You would be talking directly to one of the nodes. Since you're only talking to one of the nodes, you're not actually utilizing the blockchain. You're only talking to the node that happens to have a local copy of it. So for example, say that you have a newspaper and you read it. That's easy and cheap. But if you want to change what's in the newspaper, like the actual content, and you want to publish it, you'd have to type out the newspaper, go to the publisher, and do just in general a lot more work in order for it to be published for everyone to read. But by calling a smart contract, you're just reading the newspaper, essentially. The processing is done directly on the node, so receiving the single source of truth, so the blockchain with all of its newspapers. So now say that you're at your house with that stack of newspapers. You can get any data that is on that newspaper, and say you want to view what's been posted a few days ago. You can view and see what was posted while doing that processing yourself. The only thing that you can't do is make changes, because that won't be propagated to anyone else. You're just calling it. So in that case, it's done outside of the network. But since you can't make changes and can only view data, the entire blockchain does not get affected by it, because you're only referencing one local node's blockchain, which is always kept synchronized to the main one, like the entire one. So the node's job is to just be synchronized. All you're doing is referencing the synchronized local node's blockchain to view it, and this will in turn return the actual value. So for example, instead of returning a transaction hash, you would get an actual value, let's say 10, as a result of the transaction. And a call is very similar to the transaction. It runs on one node. So remember how a transaction runs on all the nodes? This one just runs on one. When we call an externally owned account, let's say that I'm trying to send 1 ETH to you. In this case, it wouldn't do anything. I'm not actually sending 1 ETH. I'm just instead thinking about what would happen in the case that I send 1 ETH to you without it actually happening. So in that case, you can't really do anything, but it's just to note that it's similar to a transaction, just does different things. And then there's also the smart contract, which is where most of the functions in the transaction happens. We first have a call, and that message gets converted into a message call, which then talks to a smart contract before executing on the Ethereum virtual machine, or EVM. The node itself would do this processing. So if we were to call the node and say, hey node, what's the menu of this contract? The node would essentially just go through, dig through its newspapers, and once it finds a menu, it'll be like, there it is, here you go. You can ask the node to do more things, such as like doing operations, adding numbers, whatever, but whatever you ask the node to do, it can only read it and provide it to you. Can't really change anything on the blockchain itself, because you're just calling it. So how does this look on web3.js? What a call would look is you can do web3.eth.call data. That's data as in who you're sending it to and from. You can do web3.eth.contract.function.name, .function_name.call, pretty long. Or you can do web3.eth.contract.getMenu.call. So in this case, we're calling and saying, hey, what's the menu? So if we apply this to the vending machine contract, we first request the menu, and the vending machine contract will send it to us. In this case, notice how we don't have to spend any ETH in order to get the menu. There's no cost there. So right now, here is where all the magic happens with smart contracts. What you can do is get the menu from the vending machine contract, and then the vending machine contract can talk to the vending machine products the vending machine products can return the menu to the contract, and the contract can then return the menu to us from that. So the idea of this composability is that you can have contracts that are able to talk to each other, call each other, change data on each other. And the whole idea is that you have a network of these and you're not relying on one big centralized smart contract that does everything. So let's try deploying a smart contract. Outside of the Ethereum network, so the processing is done outside when getting the menu. Essentially, you just talk to the node, and that's how it can be displayed here. You talk to the node, and the node talks to the network, and in the network, we have the blockchain. But we need to provide the address, ABI, and some data in order to retrieve this. In this case, when we say outside of the network, that means we copy the entire network onto the node, but we don't touch the blockchain. We're just talking to the node, and that node is synchronized. It's a synchronized form of the blockchain, which we can't edit. But what is an ABI? An ABI is an application binary interface, and that specifies the language you use to communicate with it. When you're referring to the ABI, it also corresponds to where the contract lives and how to talk to the contract. So essentially, we just give the address of the contract and the ABI in order to get back the menu. Now, the rule of gas is if the Ethereum network is doing the processing, it'll cost gas. The nodes on the Ethereum network are processing the data from a transaction and are updating their data on a database in order to keep synchronized with the blockchain. So anytime a transaction is published, it means that all of the nodes in the network will have to change its data. Basically, it costs gas to do everything on Ethereum. Like, for example, when you're sending a value like x equals 1, that costs gas. When you're sending a transaction, like an operation of adding 1 plus 1, the entire network is doing that, so it also costs gas. Outside of the network, it costs no gas, but you can't change the state. You can still get a value or do an operation like add 1 plus 1, but instead of having the entire network do it, you just have a single node processing it. This will dramatically decrease the cost of operation. So instead of every single computer network doing this operation, you'd only have one computer doing it. And just as a side-by-side comparison, inside the Ethereum network, you're setting the value and completing an operation. So in doing so, you change the state and there are gas costs involved. But outside of the network, however, you're just retrieving the value and completing the operation. So that doesn't cost any gas. And there's also a few different types of accounts. We have the externally owned account and the contract account. In terms of similarities, they both have addresses starting with 0xabc and they're just continuing on as the beginning of their address. They can also have balances and nonces. And in terms of differences, the externally owned account doesn't have virtual machine code associated with it because it's not a contract. And from that, it doesn't have any code associated. You can't send a transaction to something with no code and expect it to do something. But a contract account, which is also called an autonomous object, has code associated with it. It also changes in storage because it has that code with it, and it has local storage. So that's Ethereum network storage base, and it knows which space to change. It can manipulate its storage. So for the cases to call, you would have to test out what the results are. So you'd either dry run and you'd want a value that's stored on the blockchain. So for the sent transaction, you want to change the state, and this is where you'll be paying gas. This is also where you'll be, say, sending ether to another person, or if you want to verify documents, store data, anything that changes, you'll want to put that on the blockchain. And we have this yellow paper right here, and that shows the cost for each transaction is. For example, like the gas-based cost for each transaction is 21,000, like what we saw earlier. And now comes the important part. Do not store data on the Ethereum. Why? Well, because storage is very expensive, and the base transaction itself costs 21,000 gas, like what we saw in the previous slide. But storing this string at hello world itself costs 20,000 gas, and that's very expensive. This might change in the future. In fact, it might increase the number of gas as the ETH value is changing. But getting hello world costs 800 gas if it's an internal transaction. Remember, if it's an internal transaction, all the nodes in the network retrieve hello world and they have to process it all. But if you're calling the EVM or externally calling it, it costs 0 gas because you're not changing the data, you're just looking at it. Well, how expensive is storage then? Let's look at a few units first. Storing 256 bits of data costs 20,000 gas. A word is equivalent to 256 bits, which is equivalent to 32 bytes, and that's equivalent to 0.03125 kilobytes or 0.403125 megabytes. In this example, we have this nice picture of Vitalik. He is the founder of Ethereum. He is 358,000 bytes. How expensive is storage in this case? Let's say we're trying to store this picture of Vitalik in the blockchain. Keep in mind that this was when Ether was around 700, so it'll be like a lot more than this if we're comparing it to today's rate. But if we do the math, first converting the number of bytes into the words, finding out how much gas it is, converting it into Gwei before we convert it into ETH, this totals up to around 36,000 Canadian dollars if ETH was worth 700. Now it's like 3,000, so you can only imagine how high the cost would be now. So from this, don't store pictures of Vitalik on the blockchain. Even then, you wouldn't be able to store all the data because the block gas limit is only 10 million. Here, you can't store a limitless block inside the Ethereum. The transaction can't be bigger than the block itself because the block has a limited amount of storage. If the block had, say, like a gigabyte, then only supercomputers would be able to run that gigabyte. And the reason that there's a block limit is so that all the nodes on the network have to run it. So in this example, this is a bit better. This picture of Vitalik is only 8,000 bytes. In this case, if you were to store this picture, it'll cost around 800 Canadian dollars, but you would be able to store it because it's only 5 million gas and the gas limit is 10 million. You'll be able to store it for a low price of 800, but it's permanent. You can retrieve it and do whatever with it. But where can I store data? There's a few places. There's IPFS, there's Swarm, and there's also a regular database. You can store your data in a more centralized outlet, or you can choose IPFS or Swarm. And so where do smart contracts fit into decentralized applications? These are for all the developers out there. Smart contracts are like the back end of a decentralized application. So technically, smart contracts are apps, but to interact with it, it's like using an API. So yeah, just as an overview, today we learned about what a smart contract is, its uses, the differences between calling and sending one, the differences between an EOA, externally owned account, and a contract account, storing large amounts of data on the blockchain, and smart contracts as the backend of a dApp. So hopefully you got something out of this and learned something new. But if you have any questions, please let me know. I also have my email here, so you can contact me if you have any more questions about this. But now that I've gone over with the basics with smart contracts, you might be wondering, how does that apply to Metis and what does Metis exactly do? So at Metis, we give developers the ability to build on the Ethereum blockchain with low gas fees and also fast speeds from our layer 2 optimistic rollup solution. Our mission is to accelerate the transition of people to the blockchain for fair and decentralized businesses on Web3. And our vision is to create an easy to use platform that makes blockchain accessible to everyone. So we have a variety of use cases, including building DAOs, which are decentralized autonomous organizations, DeFi, dApps, NFTs, tokenization, DEX, and so much more. So Metis enables you to build all of these applications by reducing the gas fees if you build directly on Ethereum. So building on our layer 2 solution only costs a few cents. We relieve you of slow transactions by processing it in a few seconds. We also enable you to have secure, cheap, permissioned off-chain storage that is pre-built for your project needs with one-click templates and deployments. And of course, everything on Metis is all decentralized and all on Ethereum. But if you want to find out more about Metis, please visit our website at metis.io, and you can join our Telegram as well. Just scan the QR code here. But yeah, thank you so much for tuning into this workshop. If you have any questions, please let me know.